I propose the following proposition. I claim I don't know. Anyway. Hey, what's going on, everybody? This is Sean Downs, Sean for Science, and today is another great day to talk mathematics. It's not exactly morning. It's been windy as all get out pretty much all day, so there's really no hope in going outside and recording this video. So anyway, bear with me as we're inside looking at maps. Today, we are going to be talking about SL2Z once again. I promised you a proof of the proposition that I gave that the group SL2Z is generated by two matrices that we called M1 and M2 in the last lecture. I'm actually going to give you two proofs of this. The first one is an easier one will be in this video, and then another one which will let us talk about things like the fundamental domain and other kind of stuff, which is done by Sarah, which is really a beautiful proof. I'll put off for another video. Incidentally, today's proof is going to be based on the exercise, I guess like the first exercise in this book here by Diamond and Shurman. It's a good book. It's a great exercise. I'm just going to go through their version of it. So without further ado, let's get started. First, let capital gamma be the subgroup of SL2Z that is generated by the elements M1 and M2. To convince yourself that this is in fact a properly well-defined subgroup, first observe that M2 and M1 both have inverses, right? And the matrix operation, matrix multiplication is a perfectly well-defined multiplication operation. And you might recall that M2 to the fourth represents the identity element. So we have everything that we need. So let's define gamma that way as the subgroup of SL2Z generated by M1 and M2. And I claim the following proposition. For any alpha in SL2Z, there exists a gamma in capital gamma such that alpha times gamma is equal to the identity matrix. Hence, alpha is in capital gamma, and hence gamma is equal to SL2Z. Great, okay, so proof. We're going to begin this proof with a series of intermediate results, some easy lemmas that are helpful to show that will set us up for an algorithm that we will use to compute. So, lemma 1. For any alpha in SL2Z, there exists a gamma in capital gamma such that the product alpha times gamma, represented here by ABCD all prime, has C prime positive, D prime negative. Proof. Well, if they have the same sign, we simply let gamma equal to M2, which flips the bottom row, but also adds a minus sign. So now they have opposite signs. Now, in order to get the correct signage right, in other words, lower left positive, lower right negative, we might have to multiply by the negative identity element, which is, again, M2 squared. So, easy, done. Okay, lemma 2. For every alpha in SL2Z, there exists a gamma in gamma such that the product alpha times gamma is of this form, again, same form, but we'd ask/demand that the absolute value of C is strictly less than the absolute value of D. Okay, proof. Here we go. It suffices to consider the case where C is greater than or equal to D, right? So in such a case, simply multiply by M1 to the nth power for some integer n, right? So now the bottom row becomes C prime times n plus D. So in other words, C is left alone, and then the D prime gets shifted by n times C prime. And so that clearly we can choose n to be sufficiently large so that we can enforce the requirements of the lemma. That is to say that we can force the lower right-hand element to be strictly greater than C. See, really easy, not that hard. Cool. Okay. Both lemmas aside, let's now prove a little claim. So you're seeing a pattern here, right? So for every alpha in SL2Z, there exists a gamma in capital gamma such that the product alpha times gamma give us the following matrix of the form. That is to say, the lower left-hand element is 0, precisely 0. So proof. Without loss of generality, we can consider an alpha in SL2Z subject to two requirements given to us by the lemma, namely that C is positive, D is strictly negative, and that the absolute value of C is less than or equal to the absolute value of D. Okay, so if C is not equal to 0, then we can define values M and R, some two integers, such that D is equal to MC plus R. So here R is the remainder, right, of the division. So we're going to ask that R is strictly less than C and should be greater than or equal to 0. So then we can consider the product of alpha times M1 to the mth power, which gives us the following matrix, for which the bottom row is C and R. So now we can act with M2 cubed to find the bottom row is now little r and minus C. So if R is equal to 0, then we're done. But if it's not equal to 0, notice that the structure of the bottom rows is exactly the kind of starting point that we proved those two lemmas for. Namely, R is positive and it's strictly less than the absolute value of, in this case, minus C. So we can iterate this procedure over and over and over and over again until we find a point where the remainder vanishes, and that gives us a 0 in the lower left-hand corner. So one important remark here at this point, note that we are dealing with SL2Z. So all matrices in the group are going to necessarily have unit determinant. That is to say, AD minus BC is equal to 1. So if C vanishes, that necessarily forces both A and D to simultaneously be equal to either plus 1 or minus 1. So, up to factors of M2 cubed, we can represent a matrix alpha times gamma as 1, 1 on the diagonal, and B up top, an upper triangular matrix. And hopefully that upper triangular matrix looks familiar. Therefore, there exists some gamma prime, say, in capital gamma, such that alpha times gamma prime is equal to the identity matrix, because all we need to do is multiply one more time by either M1 to the B or M1 inverse to the B, and that will take us to the identity. Great, so, and as we already observed, because there's such a gamma prime, that means that alpha is the inverse of that gamma prime, which means that because gamma prime is in capital gamma, alpha is also in capital gamma since it's a group. And because alpha was arbitrary, that tells us that the whole of SL2Z must be a subgroup of gamma. And of course, gamma is a subgroup of SL2Z, so therefore they're the same, i.e. SL2Z is generated by the two matrices M1 and M2. Cute, right? Who doesn't love a little division algorithm? Anyway, that's all I've got for you today. I'm going to go outside and enjoy the sunshine and the wind. Hope you have a great day. Talk to you soon.